Hi everyone, so in this video we are going to start off in chapter 2. It's on a mathematical process. We're first going to start off with a sequence here, a couple of them, and I would like you to actually pause this video and find the missing numbers in each of them. And then when you come back and push play, I'll have the answers up here and we'll talk about how we got all of them. Alrighty, so taking a look here, in the first example, we have them going from being positive to negative, positive to negative, and they're increasing by 1. So the next will be 7, then negative 8, and then 9. Next, in the second example, we have here 7, 0, 14, 0, 21. So in between each of them is going to be a 0. So we're going to have 0, 0, and then skip over here to 0. And then as we look here, we're going to have, so we go from 21, we're going to add 7 to that and get 28. The next example, this one, taking a look, we're going from 2, 5, 10, 17, 26. So it looks like we're increasing by 3 here, increasing by 5, increasing by 7. So it looks like we're increasing by our odd numbers. So increasing by 9, increasing by 11, increasing by 13, and then 15. Okay? Alrighty, so there's this one. And then the last one. This is what we call the Fibonacci sequence. So what happens in the Fibonacci sequence, it's pretty cool. It is 1 plus 1. When you add those, it'll equal 2. If you do 1 plus 2, you add those, it'll equal 3. 2 plus 2 2 plus 3 equals 5. 3 plus 5 equals 8. 5 plus 8 equals 13. 8 plus 13 equals 21. Alright, so the next one, continuing the pattern here. So it looks like every other, there's going to be a circle in the center of our shape. Here we have 3 sides, 4 sides, 1, 2, 3, 4, 5 sides, 6 sides. So here we will have a 7-sided shape. Now bear with me, we all know I'm an amazing artist, but I'm still working on it. So we have 1, 2, 3, 4, 5, 6. Oh gosh, this is awful. Let's just pretend this is 7 sides, okay? Alright, so our first vocabulary word we're going to talk about is reasoning. So our inductive reasoning uses information from different examples to form a conclusion called a conjecture. So in the last example that we did, we were taking a look here and we were using the information from our previous numbers, the previous pattern, to form a conclusion on the next numbers following. So next we're going to talk about that conjecture, because what does that mean? So conjecture is a rule. So when we're talking about a conjecture, it's going to be an educated guess based on known facts. So as I said, the educated guess based on known info, and we will be making conjectures based on a lot of things we're going to be doing in geometry, using our postulates, definitions, and theorems. Next, we have conditional statement. So a conditional statement is any statement that can be written in if-then form. Okay, so we're going to go ahead and do an example down below of a conditional statement. Or, well, we're going to make a conjecture on this information below. So it says, make a conjecture. So as we're looking here, 3 plus 5 is 8, 7 plus 11, we get 18, 14, 12, 42, 142. Okay, so taking a look here, we're adding everything. So if we're adding two numbers, right, because we're adding two numbers, if you add two numbers, and so as we're looking here, all of these are odd numbers, 3, 5, 7, 11, 13, 1. So I'm going to actually be more specific. If you add two odd numbers, and I'm not going to just say numbers, I'm going to say integers here to be a little bit more specific. So if we add two odd integers, let's see, what does it give us? Okay, well then we know that the answer for all of them, we have 8, 18, 14, 12, 42, all of them are going to be even. So if you add two odd integers, then, right, notice I have the if and then the then the answer is even. All right, so let's move on to the next example. So it says here, make a conjecture that follows this example. And so it says, I have noticed that students with the last name A through L have been in my classroom every Wednesday since August 31st. Okay, so we need an if-then statement. Okay, so I'm going to put an if here, and then we'll just put a then down here. So I have noticed that students with the last name A through L have been in my classroom every Wednesday since August 31st. So this is saying then if something, then we have this. So if a student's last name, if a student's last name is between A and L, last name is between A and L, then they have been in class since August 30th. So then they have been in class every Wednesday since August 31st. Okay, so notice how we just took that statement and we just turned it into an if-then statement. So it's just saying if the student's name is between A and L, then they have been coming to class every Wednesday since August 31st. Okay, so just getting that if-then statement. All right, so a counterexample. A counterexample we have here is just something that proves something false, right? So it's an example. It's like kind of like a counteroffer. If you're putting a bid on a house, buying a new house, right? There's going to be counteroffers. So here we have the counterexample proves a conjecture to be false. So remember, a conjecture is an educated guess, right? So it proves our conjecture wrong. All right, so then we have here deductive reasoning. So deductive reasoning, we do this all the time, okay? So we don't just say, hey, I'm doing deductive reasoning right now. So deductive reasoning is a series of facts and definitions, accepted properties. So we have series of facts, definitions, and accepted properties. Okay, so accepted properties in logical order from a logical argument. Okay, so it's essentially making a conclusion based on facts. Alrighty, so taking a look here, let's do this example. It says, I noticed that 1 plus 5, okay, so 1 plus 5 is 8. 7 plus 11 is 18. 13 plus 1 is 14. So I make a conjecture. Okay, and so we did this. If you add two odd integers, then the sum is an even integer. Okay, so we talked about that earlier. How I've come to the conclusion, however, I've come to this conclusion using inductive reasoning. So when we come to that conclusion using just patterns and sequences and things that we previously know to get that conjecture, let's ask ourselves these questions. Can I find a counterexample? If not, can I prove my conjecture is true using deductive reasoning? Okay, so this is where you think of a counterexample. So, and that's honestly just doing more examples of odd numbers. So 1 plus, not 1 plus 2, 1 plus 1 is 3. 1 plus 1 is not 3. 1 plus 1 is 2. Okay, so doing more examples. And if not, you are going to then try and prove your conjecture using deductive reasoning, and that's when we would do a proof. Okay, so that's when we would do a proof in geometry, which we will get to. All right, so next we have here a bioconditional. The definition for a bioconditional is if a conditional statement and its converse, so converse just means when it's like opposite. So let's say that when it's raining outside, you have an umbrella. Okay, so if it's raining outside, then you have an umbrella. If you have an umbrella, then it's raining outside. So those two statements are kind of opposites of each other. Okay, so if they are true, then they can be combined into a single statement. So bioconditional we will see as something where it's an arrow going in two directions with a statement. So let's do an example using perpendicular. So if two lines form a right angle, so if two lines form a right angle, then they are perpendicular. Now, let's go the opposite direction. Okay, if two lines are perpendicular, then they form, let me rephrase that. So it's perpendicular, then they form a right angle. Okay, so these two statements here we know are true, right? So if we have two lines that form a right angle, well, we can say that those two lines are perpendicular. If those two lines are perpendicular, they form a right angle. So now let's write it as the bioconditional. Right, so we have here the bioconditional will be now if two lines are perpendicular. So not if two lines, it's two lines. So we have two lines are perpendicular if and only if, and this is that bioconditional statement. So remember I said it can be the arrow going both directions, and in words it is going to be the if and only if they form a right angle. Okay, so that would be the bioconditional statement if we're looking at these two if-then statements, right? Our two conditional statements in the converse. All right, so now the next question says, can I write out my earlier conjecture as a true bioconditional statement? Yes, we just did that right here, right? So we just did this right here. Okay, next is the amount. Goodness, Wrigley's.